Next keynote speaker will be Chris Carothers. He is a professor of computer science at Rensselaer Polytechnic Institute. And he works in the area of massively parallel computing, specifically researching supercomputing and parallel computing for the creation of high fidelity models of extreme scale networks and computer systems. He's also director of the Rensselaer Center for Computational Innovations, or CCI. And this is a collaboration between Rensselaer and IBM. And one of the key things to note about that is the AIMOS supercomputer, which is housed as part of the CCI. And hopefully he'll talk a little bit about that in his talk. And today he's going to present some recent work on composable systems, which is some pretty exciting stuff. So looking forward to hearing about it.
Thanks, Stacy. I appreciate the intro, and thanks to the committee for inviting me to give this talk today. I also have to call out my collaborators. In particular, all the results that you're going to see today were generated by my PhD student and software engineer, Neil McGlowan. Also, this is a collaboration. We have some great partners at IBM, in particular, Chayu, Jaming, and Kailesh in the IBM research AI area, as well as on the cognitive system side of IBM from Steve Roberts and Charlie Johns. Let's see. There it is. So the outline for my talk, I'm going to kind of give you an overview, at least, of our AI hardware center. I think Stacy just alluded to that. And then I'm going to talk a little bit more about, well, why do we want to consider composable systems? And I'm going to give an overview of a protocol that maybe you're not too familiar with. It's relatively new. It's called CXL, or Compute Express Link. And this is one way of possibly building these composable systems. Then I'm going to talk about, well, how we did some modeling and simulation of these future composable systems using our code's simulation framework. I'll talk then a little bit about the particular deep learning, distributed learning training algorithm we use called ADACOMP, and then show some experimental results from modeling and simulation we did, and then draw some conclusions and point us to where we hope for some future work here. So our AI Hardware Center, if you're not too familiar with it, it's a fairly large activity here in New York State. This is a $1 billion center overall, and it has sort of these 4 focus areas. So the first one on the far left is the analog AI core area, and IBM in particular has made some advances in analog cores. You can look up some of their technologies in there. They've also got some advances in digital AI cores, which some of this work actually links into. And then there's how we're going to glue it all together as clusters that they can talk about as well. And in particular, I'll give a kind of a foreshadowing or a shout out to another talk that you might be hearing a little later if you're able to stay on, is given by Kautar and Lorraine at IBM. They'll also be talking more about composable systems and the specifics of the composable system testbed that is operating inside of the AI Hardware Center. So please stay tuned for that talk. But the big message here I want to say then is that this composable systems, in terms of its research, is really cross-cutting across all of these various activities, because it's really how we might be able to glue together these systems in the future. So I mentioned AIMOS. So what's AIMOS all about? If you've ever heard of the Supercomputer Summit, AIMOS is basically a smaller variant of Summit, but of still quite considerable size. It is the 29th fastest supercomputer in the world, and I think the 7th, as of the latest top 500, most power efficient supercomputer in the world. It is a 252 node AC922 compute node. That's the style of compute node it is, and there's an arrow down that shows a blowout of it, which I'll talk about in a second. Essentially, each of these compute nodes have 2 very powerful Power 9 processors. They're very, very good at memory bandwidth, especially for CPUs, at marshaling data around. And so what these Power 9 processors do is they implement this thing called CAPI. CAPI is sort of an advanced PCI interface that allows data sharing across the processors and the GPUs that are attached to it in a way that you can't really do over vanilla PCI. In fact, if you look at the speeds and feeds on this architecture, it's something like 75 gigabytes a second to each of the GPUs in terms of memory sharing, and it is a unified memory address space. Additionally, there's half a terabyte of RAM, a 1.6 terabyte NVMe drive available on each of these compute nodes. And so then in terms of the network, this is a traditional sort of fat tree network where we've actually got two director class switches linking up all of the compute nodes via IB switches. So you can, in fact, really call this, it's like a dual plane fat tree network, because each of the compute nodes actually have something. There's actually a dual network interface card there. And I'll draw some linkages between this and composable systems shortly. This system is, of course, water cooled, which gives it some additional power efficiency. And in terms of the storage for this system, we've got 11 petabytes of storage that's capable of something like 80 gigabytes a second bandwidth. On top of this, we have another system called AIMOS X. It's a 40 node system, much smaller, but it's an x86 GPU cluster system also available. It actually is even more GPU rich than even AIMOS is on a compute node basis. It has 8 GPUs per compute node. So we're seeing lots and lots of compute devices integrated into compute nodes is sort of the current state-of-the-art architecture that we're seeing. So then the question is, and this last point sort of gets to this, why composable systems? Well, as we've run AIMOS now for a while, I can tell you that as the compute nodes have become more dense, we struggle as operators in terms of really allocating jobs and matching the resources they need to the compute nodes. And we find that many jobs can't probably really use 6 GPUs per compute node. So you're probably thinking, okay, well, that's no big deal. Share the compute node, break it up. This is observation number 2, which is users, especially our industry partners, don't want to share compute nodes. This is largely driven from security and privacy perspective, but also performance. If you start sharing nodes, then you can get unpredictable job completion times because of essentially on-node job interference. So users want to have, they want to own their compute nodes. They don't want to share, and oh, by the way, they may or may not be able to take full advantage of the hardware. And so then this leads to a potential for underutilizing of compute node resources. And we allocate these things on a compute node basis. It's either you've got it or you don't. So this is where composable systems comes in, and it can provide a technology that will extend the PCI bus such that you can configure a system on the fly to precisely match the resources that you're requesting. So you can, if you want 4 GPUs and a CPU, you can request it. If you want just 2 and your job can only make use of 2, you can request that, leaving the other ones free potentially. And so this really will potentially greatly increase the utilization of both data center, really cloud systems, but also the possibility of HPC systems in the future. So it turns out you're thinking composable systems is new. I'm going to suggest to you that it might not be as new as we think. In particular, this style of execution, the idea of you requesting a job that matches the resources of the underlying hardware is a pretty old thing in some sense. The IBM Blue Gene LP and Q family of supercomputers, going back starting in 1999, did exactly that. When you wanted an HPC job, you made a request and you got a mesh. It was actually a mesh. It was actually a torus network architecture, but you would either get a mesh or torus, in this case of homogeneous CPU compute nodes. But there was no sharing across jobs. Each job got it dedicated to its own set of compute nodes. And so you composed it on the fly. The system would dynamically allocate you that chunk of the system. You owned it, you had it for the life of your job, and it went away and went back into the pool and could be reallocated. So we want to try to recreate this, except the new twist here is we want to do this for not just homogeneous compute devices, but heterogeneous compute devices, meaning mixes of CPUs, GPUs, FPGAs, AI hardware accelerators, storage, all these different devices could be glued together to create the system that best matches your job. All right, so this brings up Compute Express Link, the Compute Express Link protocol, and it is actually an emerging industry standard where it's going to allow you to extend effectively the PCI bus to glue together these devices such that they could be made cache coherent, but I'm going to downplay that a little bit because we all know that cache coherency is a tall order, right? We've all gone down this path. One of my favorite machines I ever ran on was an Origin 2000 from Silicon Graphics Inc., SGI, and we know that cache coherency is a really tough problem to deal with. But essentially, this CXL protocol comes in really right now three major parts. It has a cache, I/O, and memory, and it really is designed to support a lot of different configurations of accelerators, memory expansion scenarios, all these things. But there's a new part. Actually, if you went to the website, you wouldn't even see it, but it is a proposal, and it's called CXL Peer. And this is what really, really excites me. And what Peer is going to offer is essentially it's a sort of an extension of the PCI bus that is going to allow you to build complex message passing topologies. So it's going to use effectively the get put style that PCI offers already, but you're going to be able to pass messages. So we're not going to have to worry about the cache coherency stuff. We can kind of hold off on that. You don't have to support that if you don't want it, but you could build very large, relatively very large networks of these CXL peers, and they could run at full PCI speeds. So what's the possibility here? Well, first off, if you look at the actual peer protocol, again, it's a message passing protocol using gets and puts as sort of the core basic operation with a 52-bit address space to work with. So you could reserve the upper 12 bits roughly for devices, giving you 4,096 possible endpoints, where each device is roughly then going to have a 40-bit or a 1 terabyte address space. That would be pretty reasonable. And then your flit size underneath is something like 64 bytes consistent with PCI. And then the interesting thing is they're talking about building pretty large RAID-X CXL switches. Not as large as what we've probably heard for InfiniBand, but pretty large. They're consistent with what we've seen out of Mellanox today, 30 to 36 ports. This is the really interesting piece, is that you could have an end-to-end latency of around 300 nanoseconds. That's the target for a 3,000 device system. So 3,000 devices all configured with 300 nanoseconds end-to-end for a message. That's actually pretty good by today's standard. Somewhere between probably 2 and 3x or better from what we've seen out of InfiniBand, depending which grade of InfiniBand you're talking about. And then again, you're also getting the bandwidth advantages of running strictly over PCI for this. So then how are we going to model this? Because these things don't exist today. So we've been doing a lot of work with the Department of Energy on a project called CODES. CODES is a framework that's going to allow us to model these types of systems. It's a massively parallel event-driven framework. And we've been modeling all sorts of different types of networks. In particular, we've done the torus, so that's what BlueGene was. We've done Fat Tree, which is what our AIMOS has today. We've done this other network I'll tell you a little more about, Dragonfly and variants of it, like a Megafly. We've even done Slimfly, which is a theoretical network that actually Torsten did, one of the previous speakers. So we've done a lot of these different networks. We've also done storage modeling, burst buffers, disk storage, and then we can drive onto these models a lot of different workloads, either the real traces that come from them. So we've done a lot of work with the design forward traces coming out of the Department of Energy. We've also built a synthetic workload modeling sort of language, if you will, that allows you to sort of specify in C code or C++ code a synthetic workload model. So for example, LAMPS, a molecular dynamics code. We also have MILK, another HPC code. So all of these things are part of CODES. Now, CODES rests on top of ROS, which is actually our parallel simulation engine. And all of these things that I mentioned is parallel. We've actually scaled ROS up to something like nearly 2,000 MPI ranks on what was the Sequoia system out of Livermore. So all of this, the system is very, very scalable and allows us to run these highly event-dense models. Now, our target system, this is the target composable system that we're going to be modeling, is we're going to take essentially a building block of what you might think of as a node today, something like a DGX1 box from NVIDIA. That could be a building block. And then what we want to do is point out and say, well, let's compare that with what if we could build a really truly composable system like the one we want to build, that would be in one of these, we'll call it a Dragonfly topology, which is actually, we picked it because Dragonfly is going to be the first exascale supercomputer network of record. It's going to be coming out of Argonne National Labs. In the not too distant future, it's going to be Aurora. So with that as our composable system targets, what's our workload? So IBM has been doing a lot of work in this area, and they've come up with a different style, and I'll talk a little more about it, of deep learning training approach, and it's called ADACOMP. It's one of the first ones. They actually have a follow-on one called ScaleComp, and that's going to be running the ResNet 50 benchmark. So let's look at our super tree architecture, and it looks just like the architecture I kind of showed you, where we take a bunch of CXL switches at the bottom, attach our GPUs to them, 2 per CXL switch possibly, and then we begin to increase bandwidth as we go up the tree like you would normally do. Normally what we see in these architectures is the CPU in the middle, so we kept that. We're going to argue against that, to be honest, because quite frankly, what CPUs are doing in these architectures is they're just giant data marshalers, and they're kind of expensive to be just left doing that. And then we'll have some connectivity up to a CXL additional switch, so we could keep extending the PCI bus out. And the point I want to make with this is I'm showing just 2 of these 8-node subtrees. What we could do is then replicate this out, and you could keep building up more CXL switches, and we could create a 3,000 endpoint system this way. So that's one way to do this. Another alternative is to do what we've been doing in HPC for a long time now, is look at alternative architectures really from the ground up. And so we could say, well, what if every endpoint, device endpoint, really just directly plugged into a switch? Get the CPU out of the middle part, and we begin to use a lot of the research that we've been doing over the years in really good, well-balanced HPC network topologies. And a Dragonfly is representative one. Obviously, there are others. You could be looking at a factory. You could be looking at a Slimfly network. All of those would be very good as well. So we were picking Dragonfly just as an example. So Dragonfly in particular is a hierarchical structure. It's got a bunch of local group routers that are all interconnected. So the circles here are the routers. The little tiny boxes are endpoints. So you could think of those as endpoint devices. So in this picture, you could think about, I don't know that we would do it this way, but say the brown nodes here are going to be compute nodes, or sorry, CPUs. Red over here could be GPUs. Green could be FPGAs. Blue could be maybe some memory storage, and green over, or sorry, the darker blue could be some SSD drives as a possible option. You might not do it that way for a lot of different reasons, but I'm just sort of pointing out a possible, just to give you some reference point of what is a possible layout of an architecture for a composable system. So again, the groups are all to all, and then it goes all to all across the groups. So essentially, there's a nice well balance of local channels with global channels in this architecture, along with a number of supporting a number of terminal nodes or devices within each of the groups. So then this is the actual deep learning algorithm called ADACOMP. It stands for Adaptive Residual Gradient Comparison. You can see sort of the 2 algorithms. There's algorithm 1 and 2 here. The takeaway, without going into too many of the details, is that this algorithm essentially is a compression algorithm that's going to allow essentially the residuals to be compressed across all the layers, so for fully connected and recurrent layers as well as convolutional layers. So typical compression before had been limited to not considering all the layers, but it can do all of the layers somewhere between 40 and 200x without any noticeable degradation in accuracy. So that's the big sort of takeaway as to what this algorithm does. Now, the way it works, interestingly enough, is if you look at what you would do in PyTorch today for this, and you're sort of in exchanging the residuals, you would probably be doing an all reduce, but a number of them, many more than you would here. So we're shifting from an all reduce form of traffic to an all gather form of traffic across all of the workers or learners. The effective reduction, because again, this is what the local rate is. So if I got a 100x reduction in data that I'm compressing, I have to then share that full data across everybody and all gather. So let's say I had a 100x reduction, but I've got to share that across like 10 workers. My effective reduction is about 10x over what you would have incurred in the actual all reduce traffic. So there is still a substantial savings in overall network traffic, which is one of the limiting factors with this. Now, so what we did is we actually built a working synthetic workload model of the ADACOMP algorithm, and we were actually able to then use traces that came out of the real algorithm. So the model actually will generate the actual right point-to-point calls, but then the numbers of what these calls were for ResNet 50 came from a real running trace of ADACOMP, and so we ran that through our code system. And so these were the experiments we ran. We have our subtree experiments where we were varying across a large number of bandwidths. These are at the super links up here. All the other links kind of remain the same in our basic building block, but we were able to go from 12.5 to 100 gigabytes. This is sort of the main network configuration with 64 byte packets, switch delay around 90 nanoseconds, which is sort of consistent maybe for this CXL technology. The buffer sizes were with what we would expect as well. And then we also had normal links. The short links were 10 nanoseconds, where the longer links would have been 100 nanoseconds, noting the distance between things. Similar for our Dragonfly network, we had 3,000 node endpoints, of which we were only using 16 of them, but we would randomly assign the workers within a single group, so one of these circles. And so then this is a similar configuration where everything else was held fairly the same as what we saw on the other, along with our buffers and things like that. The one difference is where the way a router gets sort of split apart in terms of some ports on the router are used for global links, local links, as well as terminal links. So in terms of the first line of results, we compared the super tree. Again, we had 16 nodes, but we're going to 16 workers. We're running over, in this case, just 2 nodes going up into the single super tree. And we compared that with first a baseline case going across of, imagine you've got a DGX2 box with 16 GPUs in it. So all 16 fit in one node running at PCI speed. And this is what we got. So we see that the total communication time to run ResNet 50 was getting well above 8 milliseconds, which is, this was for one effective iteration, by the way, of full iteration of ResNet 50. So we're not doing it for all the iterations of it, but just one. And so you're seeing that at 12.5, it's around a little over 8, where we shrink down. It takes us to get to 100 gigabytes a second of those uplink speeds before we can get down below what we would get out of one box. And so this is the problem that we see is if you keep your deep learning within a box today, you get pretty good performance. But the second you kind of go out the network and you run into bottlenecks, which is kind of what we're seeing here, you see a tremendous impact in terms of the overall communication time. So now what happens if we run it on a Dragonfly? Right out of the gate, the Dragonfly, even if I use just regular PCI speeds at 16, PCI Gen 3, we're already below what we're expecting, of course, to get out of the self-contained box. And even the 12.5, which is what it was running over there, it's fairly consistent. So I can connect up all the things over a Dragonfly link, and I get sort of similar speeds, and then it gets even much better. So in fact, the Dragonfly can actually be, in some cases, 4x faster than the SuperTree for the same uplink speed. So this topology is has more bandwidth diversity, is richer, and a lot more capability. And so the SuperTree is a base topology. You really need to give it a lot of bandwidth right up front for those links, for each of those nodes to kind of do well. And we actually see that, I think, in the real, if you look at a DGX2 box, I think they have 8 InfiniBand links coming off them to get enough bandwidth to them. And it's even unclear if that's probably enough today. But this sort of gives you a sense of the distribution of messages across the entire system in nanoseconds. So we see that on the Dragonfly, all the traffic is compressed down, and then everything is delivered in 75,000 nanoseconds or less. I know that sounds like in nanosecond scale, but nanoseconds really start to matter when we're talking about the number of traffic. Excuse me, sorry. We're talking about the traffic that's going through the system. Similarly, for at 25 gigabytes a second, again, the PCI super tree well above 10,000 nanoseconds, while the Dragonfly is well below 5,000, probably around 3,000 in this case, 3 to 4,000 in there nanoseconds. And so you can see the distribution. What's interesting in the super trees, you see the hump here, and that's indicative of the bottleneck that's happening on those uplinks. So we see a surprising amount of traffic being bottlenecked there and sort of languishing there. What's also interesting is when you look at these graphs, they don't tell the full story in the sense that they're only figuring the end-to-end latency once the packet is injected. Whenever you have a lot of congestion in these networks, we're using a token flow control mechanism. If there's no room in the network, then the packet is actually held back at the terminal or the device that would be trying to send the data. So until it's injected in the network, time doesn't even start. And so that story actually isn't even being recorded here. So we keep seeing this sort of phenomena where we still see that hump, but it kind of begins to go away. And then finally, once we get to 100 gigabytes a second, we finally see a curve that looks like what we were seeing when we were running on the Dragonfly network in terms of the overall latencies. And so what's interesting is if I go back and compare 12.5 gigabyte technology through and through to the 100 gigabyte uplink technology, which also, by the way, it was using the PCIe links, it takes this level of performance at the uplink to get and beat the Dragonfly and sort of an older version or an old version of 12.5 gigabyte network technology, just as a point of comparison. So this leads me to some conclusions. One, I think these results, hopefully they've encouraged us, hopefully they encourage you, that these systems really are going to provide a new opportunity to improve both the performance, this is I think the cool thing, plus utilization of an extreme scale system. So I think there's a double win story here that we're hoping for here. The big thing that I want to take away as well is that we want to rethink the notion of what a compute node is. Don't start with existing compute nodes as a design point. In other words, these fat nodes need to be broken back down. The CPUs should not be used as a switch, I think. We need to be pulled out, and that the compute nodes need to be pulled down and directly connected into the network, just like the GPUs, FPGAs, and whatever accelerators you might want to be using in the future. Some interesting research questions, and this is just a quick list. I think will open up a lot more. First off, and I kind of alluded to this earlier, what's the right mix of compute devices? Where should they be? If you were having a 3,000 compute device composable system, where should you position the devices? What's the right mix of CPUs and accelerators? Where would you then plug in your InfiniBand network? You're still going to have it. It's still a great thing to have. And in fact, the interesting thing with InfiniBand is it's really moving to being compatible with Ethernet in the data center today. So this would be great if the InfiniBand Ethernet plugs into this in a new way that allows it to be much more extensible than just being strictly the HPC network. And in fact, we could take some of the HPC lift off of the InfiniBand network and put it into the composable system. So it really raises some interesting questions in terms of where might we include InfiniBand. In terms of our direct future work, we're going to be going and moving to the more complicated algorithm, but it's shown scalability to 128 workers. In particular, ScaleComp still looks like the original all reduce approach that we've come to know and love maybe with PyTorch today, but it has even more compression than what ADACOMP can do and scales beyond what ADACOMP can do. And then I think the real question of the day, could we build these, and would these types of systems truly be cost effective? Meaning, if I save 30, 40% in terms of if I gain that utilization, is that worth it to build this system? Or is this system going to be something like 2x more cost to build and just not be cost effective at all to build, despite having these performance and utilization advantages. So that will be, I think, another interesting area going forward. But with that, thank you so much and appreciate the opportunity to speak with you today.
Great. Thank you very much. That was really interesting. Does anyone have any questions? If you do, you can feel free to just unmute yourself or type in the chat and I can relay. Well, I'll let people ponder for a second, but I have a question. This might be a little out there, but I was wondering, is there any job or workload you think where, you said these could be configured on the fly, but I assume that means like before you start a job, but is there any case where you would want to do dynamic reconfiguration in the middle of a job, or is that something that might be beneficial?
I think absolutely. I think in HPC we would love to be able to do that. In fact, for a while there is or was in the MPIO or sorry MPI message passing standard an ability to do some of that, but it never really I think took off with the vendors per se, and it's never been something at least I've seen supported for real in any of the production environments. But in this case, it might be something useful where if a job went through phases of not being able to fully utilize the system, you could claw back some of that resource and it could shrink for some period of time and then it grows again. So I think as resources become more and more expensive to manage, effectively utilizing them correctly and matching the compute needs to the job will be increasingly desirable, especially probably to the cloud vendors where they're wanting to squeeze out every bit of efficiency in terms of job throughput for their systems. On HPC, we have probably a similar but slightly different metric of performance.
Okay. And then I guess along the same lines, is there a possibility of automating the selection of the systems that you want to compose? I guess in some sense it's like, or do you need to know ahead of time? Like I mean, can you do like this just in time compiling your system?
Yeah. So what you're saying is I want an AI engine that's going to help match my job to my resource. And I think that's ultimately probably something like that, where it would do pattern matching on the job logs, and then it could, or something like that, where it looked at job histories, job performance. It even could take in, job interference. We're actually considering some of these things. We have some work that's pending with the Department of Energy, but it's looking at some of these things of how you would schedule, not so much a composable system, but just this question of how to better schedule and match jobs to available resources. So it's still very much an open question on systems today. I think composable systems will just add a new dimension of complexity to it.
Oh, yeah. I mean, it sounds kind of like with the just VM kind of allocation to physical machines, but a much harder problem now because you have so many more choices.
Yeah. We'll be dying under the avalanche of too many choices.
It's not a bad problem.
Yeah.
All right. Did anyone else have any other questions?
Yes, I have a question, if I may. So this is Kautar. Thank you,
Kautar.
Chris, for the wonderful talk. Like you mentioned, it's a great, introduction to our upcoming talk about the composable. I have a question about the codes simulation. So is it, was it simulated, on multiple nodes? Was this run, on the AIMOS supercomputer, or it's all done in simulation, how you define the workers and
It's all done in simulation, although I think, Neil, we have run codes on AIMOS. So it does run there. But I think we were actually running on some other system to generate these results in particular. What's interesting for codes is the super tree was actually a relatively small model. And so it runs very, very quickly for us. So we can, I'm only showing you a fraction of the results that Neil generated for us.
Sure.
So, but we're hoping to be able to generate a lot more results and share that in the future as well.
Very interesting. And also saw that you use PCIe Gen 3. Have you considered the fourth generation?
Yeah, so we were looking, so if you look at some of our other graphs, we were looking at, well, what happens when you go from 16 So what Neil graphed for us was 16, 32, 64, 128. So those correspond to the next generations of PCIe.
Okay, great. Thank you.
Great. Are there any other questions? There's a question in the chat. Is anyone working CXL switches?
Yes, they are. And on top of the CXL switches, I just saw it's the Neoverse. I think it's either ARM, but I saw it come from AMD. But there's an ARM Neoverse. I think I got it right. V1 processor that has CXL extensions in it already. So they're already providing it to be programmable for CXL. So that apparently does exist today. It was just announced a couple days ago.
Great. Any other questions? All right. Well, thank you very much for that really interesting talk. Appreciate it. Good to see you.
Thank you, everybody. Appreciate it.
Yeah. All right.